In computer vision, most teams will pick a model, train it, and try to make it work. It's the wrong approach. The real question is not how well one model performs, it is how quickly you can learn what holds up in the real-world environment. In real-world detection problems, like drone tracking, the environment does not stay consistent. Distance of the object changes, lighting shifts, backgrounds vary, motion induces blur. If you optimize your model too early, you're optimizing against an incomplete understanding of the real-world environment. So the priority at this stage is not early performance, it is building the data foundation that makes performance and generalization reliable. In this example, we are working with EO drone footage from the anti-UAV dataset. The objective is simple. Start with minimal labeling, expand through discovery, and benchmark multiple model architectures as the dataset evolves. We begin by labeling just a few instances of the drone. Not hundreds, just enough to define the object. From there, the system begins identifying similar candidates across extracted frames. This candidate-driven discovery is where dataset growth begins in the Iris platform. As new videos are introduced, the dataset begins to evolve. The drone is now seen under new conditions. We see the drone appear at greater distances, smaller with less detail. The drone can be a different shape, a different color. Small drones are notoriously varied in their appearance. Even if it's a similar drone, it can appear with different backgrounds. Each of these variations adds a new dimension to how the object is represented. Not every candidate is correct, but correction is fast. Even when a box is slightly off, it can be adjusted in seconds. This keeps the dataset clean while still allowing it to grow quickly. You are not slowing down to maintain quality, you are maintaining quality as you scale. As the dataset grows, the conditions become more difficult. Blur, city backgrounds, partial visibility. These are the scenarios that determine whether a model will generalize or fail. And this is where the dataset quality matters most. By the time we reach this point, the dataset is no longer defined by a few labeled examples. It reflects the range of conditions the system will encounter in the real world. At around 500 annotated examples, we run the first benchmark. Not to finalize a model, but to understand how different architectures respond to this dataset as it exists today. At this stage, the dataset is still evolving, so the goal is not to optimize a single model, but to understand behavior. Instead of committing to one approach, multiple models are trained under the same conditions. This creates the opportunity for a controlled comparison. Each model sees the same data, the same splits, and the same constraints. What you get back is not just a performance score. You get insight into how each architecture handles variation, which models detect consistently, which ones miss under certain conditions, and how those differences begin to emerge early. For example, when we compare evaluation results frame by frame, something important stands out. Faster RCNN often assigns a higher confidence score on correct detections. But at the same time, it is more prone to missing detections entirely. This is the trade-off. Confidence does not mean coverage. We select the top performing model, the small YOLO V8 in this instance, and deploy it in the system. Now we can test it on new data, and this is where things get interesting. The model performs well, but it does not capture everything. Even after deployment, discovery continues to find what the model misses. In some cases, the model detects the object, but the candidate process produces a better bounding box, more precise, better aligned to the object. In other cases, the model misses entirely, while discovery surfaces multiple candidates for validation. Some are correct, some are not, but the signal is still there. By the time we reach 1,000 annotations, the dataset reflects a much broader range of scenarios, not just larger, but more representative, more aligned to real-world conditions. So, the benchmark is repeated. Now the comparison is no longer based on a partial dataset. It reflects how each model performs under more realistic conditions and provides greater insight into understanding how performance evolves. Most workflows treat dataset creation, model training, and evaluation as separate steps. But in practice, they should happen together, because optimizing early does not make a system reliable. Learning continuously does.